Yeah, you can see how I like a nice clean slide with very little on it so people don't have to read much. It's my style. Evan tells me I should try to be lean and mean, but I just try to be bloated on my slides. It's a complex trait study, you know. So we're interested in, I highlight Shuhita. She's been involved in this from just about the get-go. Evan mentioned this project started back in about 2012. I consider it having started even a little bit earlier than that. Collaboration with Johan Orix. And several of these papers have already been mentioned in the previous talks. Shahita's paper, which is everything but the genetics, just to review that briefly. Evan's already talked about where we pointed to this paper. Base pointed to the paper over there. Those are all EXV. Oh, too close? Oh, closer. Oh, okay. And then the paper in the lower left corner is a recent paper using a different population called the het3, more like the HS or the DO that we've used to validate and extend. Okay, so I don't have to belabor this, but we're up to about 120 extant strains. Nominally 152 were sequenced, or 154. I think it's pretty easy to get 100 of these strains if any of you want them. They've all been sequenced short read. Now we're moving to long read using both Oxford Nanopore and Revio and whatever hi-fi data we can get our hands on. Let's see if the pangenomics group is here. So there's Enza. Eric was here.
Yes, yeah,
that would help.
Yeah.
Yeah, it is on. Testing 1, 2, 3.
Talking to the mic.
Even more. Oh. That's amazing. Okay. Normally I'm way too loud, so I'm trying to not be way too loud. So we're going to have an unrivaled or almost unrivaled T to T for this family, thanks to a lot of people, including Abe, who's provided a lot of hi-fi sequence data for us as part of a collaboration. And what we've been doing is mapping both the chow diet and the high-fat diet, using the BXDs primarily, the females you've already heard about. And then we've also been using the het3, which has the same parents. So there's the father of the BXDs, there's the mother of the BXDs, and then two other parents, Phelpsy, Bailey J, and C3H for a four-way or tetraparental cross for validation. You've seen this, don't need to belabor it. This is just a review showing the generic average effect of high-fat diet. It's a bad thing, it's not a tragic thing. On average, it reduces lifespan about 2 or 3 months. It's quite significant if you translate it into humans, 7-year loss of life. The R squared between these two populations at the strain level is not very impressive. So it's a 0.051 correlation between chow diet on the x-axis and high fat. Sorry, you can't see it, but you can certainly look at it in Gene Network. There are some exceptional strains where they live quite a bit longer on the high-fat diet, which is basically the story you just heard from Kara, right? So there are lots of exceptions to general truisms about what would be good to do or bad to do. You're familiar with this from Evan's work, so I just wanted to ping that briefly. Here are the data that, updated version of the data that were in the white paper of 2021. Just showing the impact with a reference on the chow diet, and then the lifespan of individual animals by strain. On the high-fat diet is the non-reference or the non-ordering strain. You can see some interesting patterns here. I don't think this is significantly different from what you might expect, almost from a random pattern. But I just want to highlight the fact that over here, you can see that there are very for the chow diet animals that don't live very long, say from an average of about 400 days to 500 days. There's not enough much difference between those on the chow diet and on the high-fat diet. Over here, you can see a deficit or a significant drop in longevity on the high-fat diet. And there are a few strains, as I mentioned, that manage to live quite a bit longer on the high-fat diet. No surprises there, really. It's good to see the range of variation because it means that some of these questions make sense. So using large sample sizes and replication, can we map loci that modulate lifespan? What are effect sizes? This was the issue that I mentioned in my question to Amelie. Heritability for longevity is poor. Probably the highest estimates I've seen for a standard segregating population are about 0.2 to 0.3. With the BXDs, you can artificially boost it to 0.8, 0.9 by simply sampling over and over again, with the recognition that they're batch effects that you have to keep track of. To what extent are lifespan loci modulated for diet? Are they truly specific for diet, or do they just modulate an existing panel of what we call vital loci for lifespan loci? Are they mapped precisely enough to warrant testing candidate genes? That's been a problem for our community from the get-go. And I will say yes is the answer, they are. This is an interesting new twist that I haven't seen in the literature before, so they introduce you to. Are there life insurance loci? So about 20 years ago, life insurance companies woke up to genomics and said, wouldn't it be cool to genotype everybody and see who we shouldn't give insurance to? Wow. So if you have an ApoE4 allele, forget about it. This is fortunately the GINA prevents us now. And I guess the final question is, can we validate these loci that we find in the BXD using a completely different, almost completely different resource, the UMHET3? The techniques I'm going to show you are either using the strain means, medians, quantiles, whatever you have per strain, or we can actually fit a linear mixed model with the individual data and cofactors. Here's what the data look like. The first method I mentioned, just mapping the strain means. We have 85 strains that we use for mapping on the chow diet and 82 on the high-fat diet. There are actually more strains coming online. The second method is to use all of the individual data and just, again, fit a linear mixed model, including a lot of F1s that we started making. We've made F1s between short-lived and short-lived and long-lived and long-lived, just to see what the impact of heterosis is. And then we're going to actually do this sort of actuarial genetics. We're going to say, what if we include all animals? Every one of 1,921 animals. Or what if we cut here at 1 year of age and just use the oldest 91%, the oldest 70, the oldest 45%. And you'll see some interesting trends there. And if you were running an insurance company for mice, you would want this data, possibly. Okay, so first, mapping on a chow diet. I should get that slide from whoever showed the thinking man, very depressed. So this is a kind of mapping that after 10 years you would go, oh. I rarely get depressed, but and I didn't get depressed in this case either. But you can see I've got a bunch of question marks. We go, you know, Carl Broman and Shaunak Sen aren't going to let me get away with this, unfortunately. But here's the good news. So you can then ask, I've got weak signal that looks a little bit intriguing here, but what if I now switch over to the other diet? What do I get there? And here, there's at least one exclamation mark. And it's on proximal chromosome 1. It goes from about 0 all the way to about 45 megabases. And it's a whopper by my loose standards with a peak log there of about 5.1. It's a complex. So the just so story is that whenever you find a QTL, there's one causative variant in that QTL. That's a just so story. There are going to be a dozen in there. So we think we've already divided this into at least 3 subloci that we think are hanging around in that proximal 45 megabases. This is a distribution perfectly normal, but you can see these animals are going to die of early onset lymphoma, maybe not so interesting. You really want to know, what are these animals dying of? So that's where the second part comes in. But before I get to that second part, I want to zoom in on this Vita 1A, Vita 1B, and Vita 1C. For those of you naming QTLs, please use the chromosome number, because as soon as you get up to 5 QTLs, I guarantee you won't remember which QTL is which, unless you name them in more or less this kind of method. So Here's a zoom on it, just show you no big surprises there. But you can see even here that vitamin 1A and vitamin 1B do look independent, the big trough. LD blocks and BXCs are big, but they're not big like an F2 would be. So these are really separate loci. These are probably separate loci. So we're just accommodated to the complexity of this locus, and are going to assume there are at least 3 causes, maybe way more. Vita 1D is a locus we found in UMHET3 that we don't see in the BXDs, which is not a surprise. This is the validation, just part 1 of it. So this is all data from the UMHET3. These are, we have different ways of mapping. So Vita 1A, Vita 1B, and what I called Vita 1D today. The cutoff age I'll introduce you, but it's the actuarial genetics. We cut off here at 860 days, so those are relatively old animals. In this way, we're using a standard 4-way mapping using Carl Broman's RQTL, and we have a peak at 3 megabases for Vita 1A. Vita 1B, we have a peak at about 24. There is some overlap, but we're pretty sure it's different from the BXD data that I just showed you. And then in the UMHET3, we have one that's way off in the ozone that I highlighted at about 120. We had a really good candidate, and we still have a really good candidate in Vita 1A. I'm sorry, Vita 1B. It's a succinate dehydrogenase assembly factor that's part of complex 2. It's known to regulate oxidative stress in the mitochondria. It's known to be modulated by a high-fat diet. So it's a fabulous candidate. Of course, there's this thing called the narrative potential of candidate genes. So I have to admit, this one's pulled me down into a vortex, and I love the narrative potential of this gene. We'll see if it pans out. But there are the C. elegans results from Johan Horwitz's group that do show that modulating this gene. Sorry, I have to go slowly here. Okay. So this is now mapping the individual data. You can see the Vita 1A complex B, 1A, B, C, and D. And now I'm going to cut off every animal that's under 12 months of age. And I just want you to keep your eye on this locus on chromosome 15. And so removing the early deaths really does help quite a bit. And we see that consistently in different populations. So you don't really want to throw in all of the early deaths. The first 10% probably don't help if you're interested in mapping true longevity lifespan loci. For those of you who follow the QTL-rich region, this locus here is essentially cloned already by Jake Lucis. That's an application. And 15 has some mouth-watering candidates. So people, the BXCs are not famous for their ultra precision in the sense of the DO and HS might be, but look at this little locus. It is about 5 megabases stretch. But the beauty of it is that if you look down here, this is the orange hash where mom and dad are segregating and the kids are segregating. And all of this, you can basically, if you're like me, you have my personality, you can throw it in the trash. If you have Shaunik's personality, you have to look at it very carefully. But there are 3 fantastic candidates here in this polymorphic region. PDZ-D2 is by far the best. It actually modulates insulin basal secretion level in the pancreas by beta cells. And it's been knocked out, and it does all kinds of messy things to insulin levels in response to glucose. So I think that, again, has a lot of narrative potential. This is one other final locus I'm going to talk about. If you now trim so that you're only looking at the oldest 45%, so this is now doing actuarial genetics for Rob as a 71-year-old saying, should I insure him for 10 years or 20 years? You're not going to go 30 years, unfortunately. So this one's interesting to me personally. And we have a fabulous candidate in it. We see this both in the BXDs and in the UMHET3. It's pretty amazing in the UM3, as I think I'll show you, but it has. Okay, so this is the famous mutation that made Kenyan famous, the DAF mutation in the IGF-1 receptor homolog or ortholog in C. elegans. This is a knockdown of hyaluronidase 1, 2, and 3 homolog in C. elegans by HY1 is what it says there. And you can see that if you measure this is at 25 days of age, just watch the worms wiggle around. So it's a motility assay. And you're just looking at the difference between the Sioux Kenyan DAF1 and the hyaluronidase. And you can see they both make it out to 35 days. And if anything, the knockout here is a little bit more vigorous than DAF1. So again, a lot of narrative potential there. 1 minute, I chopped my head off. Okay, here's a cool slide. You're never going to know what it's about until the paper comes out. But conclusions. So we've mapped about 5 vital loci in the BXDs. We've got about 35 in the UM-Het3. The answer to the questions, clearly diet does modulate the amplitude of most BXDs. We're not quite sure the diet-specific loci. I suspect there are, but I wouldn't say we have screaming good evidence yet. Candidate gene analysis definitely worthwhile, and those are the candidates that I highlighted. Yes, there would be loci that would be interesting for Radica, maybe. Not for Radica. I hope the GINA law protects us here in the United States from abuse, but in Australia, there's no law against insurance companies. So it's kind of an informal agreement. And here are all the people to thank. You've heard from many of them. So I'm done.